Hi everyone, I'm Zhijian from Tsinghua University. In this work, we propose joint stochastic approximation and apply it to learning discrete latent variable models. This is a joint work with my student Yunfu. First, I introduce our motivation, then the new method at GSA, and especially connecting it to the classical EM algorithm, finally the experiments. The core problem addressed in this paper is how we can effectively learn latent variable model P theta for observation X and discrete latent variable H with parameter theta. Such models are widely used. Here we use graphical model representation. The circles represent random variables which should be differentiated from the rectangles which represent neural net states. The left shows the sigmoid belief net, which consists of multiple layers of Bernoulli variables. The right shows the variational autoencoder, which consists of multiple deterministic neural net layers to define the conditional distribution of X given H. These two are illustrative examples used in this paper. Currently, variational methods are the main methods for learning discrete latent variable model, which basically introduce an inference model QV to approximate the two posterior and to maximize the variational lower bound, also known as alpha. There are two annoying difficulties with current variational methods. First is the harm variance in estimating the gradient of error with respect to phi. And second, current variational methods indirectly optimize the target log likelihood. This leaves an uncontrolled gap between the target and error. It is highly desirable that we can reduce the effect of the gap on model learning without increasing the complexity of the inference model. In this paper, we show that the two annoying issues are inherently related to choice of optimizing the error. They can be gracefully addressed in a new method based on SA theory of Robbins-Monro type. Here comes the new method of GSA. In GSA, we propose to directly maximize the marginal log likelihood and simultaneously minimize the inclusive divergence between the two posterior and the inverse model. Fortunately, we can use the SA framework to solve the joint optimization problem. Here is a brief introduction to SA. SA provides a mathematical framework for solving root finding problems stochastically of lambda being equal to 0. Lambda is a d-dimensional parameter vector. F lambda is defined as an expectation of capital F. Capital F provides d-dimensional stochastic measurement of the mean field function F lambda. The expectation is taken over random z, which is distributed according to p lambda. So intuitively, SA solves a system of simultaneous equations f lambda being equal to 0, which consists of d constraints for determining d-dimensional parameter vector lambda. Algorithm 1 shows the general SA algorithm, which iterates Monte Carlo sampling and SA updating. It should be noted that algorithm 1 shows the SA with Markovian perturbations, which is more general than the non-Markovian SA. In Markovian SA, we check the ergodicity property of the Markov transition kernel. The convergence of SA has been established under conditions for the mean field function f lambda, transition kernel k lambda, and the learning rate. In developing GSA, the starting points are the two objective functions from which you could obtain the two gradients with respect to theta and phi. Suppose there are a number of n data points x1 to xn with corresponding hidden variables h1 to hn. For reasons detailed in the paper, we introduce an index variable kappa, which indexes the current age under sampling. With these notations, we could define capital F, and we can show the expectation of capital F equals to the gradient, and so we can apply SA. So in the Monte Carlo sampling of GSA, we draw kappa to pick the data point and use MIs to draw H kappa. In the SA updating, we use X kappa and H kappa to update the parameters. Given current sample, the MI sampling works as follows. It is important to note that the MH ratio does not involve the intractable term P theta. The new methods may seem unfamiliar to you, but the connection of GSA to the EM algorithm will let you appreciate the new method very well. The EM algorithm consists of E step and M step. When M step is intractable, people propose to perform gradient ascent over theta. When the A step is intractable, people develop SAEM, which is basically an application of SA on solving the gradient being equal to 0. It iterates Monte Carlo sampling and SA updating. When the sampling from the posterior is intractable, people develop SAEM MCMC by applying Markov move. However, the proposal of the transition kernel is fixed, which may limit the MCMC efficiency. In this paper, we propose to couple SAEM with an adaptive MCMC procedure. The inference model QFI acts like an adaptive proposal adjusted from past realization of Markov chain. Here are some comments on novelty and significance of GSA. To the best of our knowledge, GSA represents the first method that covers SA-based model learning and SA-based adaptive MCMC. And the second, the model learning of theta and phi are coupled, evolving together to converge. It should be noted that we do not need to run the MCMC transitions sufficient long in each iteration. Thus, the training complexity of GSA is close to that of variational methods. We conduct 3 experiments. The first experiment is learning with ballooning latent variables. There were 3 types of models, and we experiment with different existing methods. The second experiment with a categorical latent variables or MNIST, and it can be shown that the gradient variance of phi from GSA is smallest. The third experiment is with structured output prediction. All the 3 experiment results are similar, which shows that GSA consistently outperform recent competitive algorithms with faster convergence and better final likelihoods. Reproducible code is available at this URL. Thanks for your attention.